Hey everyone, this is going to be the notes for chapter 13.2. 13.3 and 13.4 are coming, but 13.3 is really big, so I decided to have it as a separate thing entirely. So we're just doing 13.2 right now. There's going to be a video posted for 13.3 a little later, and then 13.4 a little after that, because I have to do some recording. Either way, we're going to start with 13.2 though, with Euler paths and Euler circuits. Last time I mentioned that a path is a sequence of vertices that corresponded to a sequence of connected edges that were in a particular order, and they have to form a sort of path in the traditional meaning of that word. And then we also went on to talk about a circuit, which is just a path that ends where it begins. It kind of forms one sort of weird circle kind of thing. It doesn't have to look like a circle, but it ends up being in one pattern. By the way, this means that when we're talking about a circuit, we can describe a circuit in more than one way using just different letters. And I'll give an example here with this graph. You can see that there is a kind of a triangle thing of A, B, and D. So if I wanted to talk about the circuit, I could talk about it as ABDA. That would be starting at A. Or I could say BDAB, which is the same triangle, but it just starts at a different point. And in fact, we can also go in reverse. So ADBA, that just starts from A and goes down rather than right, is also the same triangle. So with that, we can kind of say that ABDA is a circuit and CABDA is a path. That's CABDA. And one of the things I didn't mention last time, but I feel like I should mention this time, is that a path can't reuse edges. It's not allowed to. Otherwise, it doesn't really make any sense. So even though that's true, paths and circuits, they can't repeat an edge. That doesn't mean that you can't have more than one edge between two vertices. And in this case, I've put 2 between A and D. And we can talk about paths that would be impossible in a graph that didn't have this particular feature. And we would just use each edge a maximum of one time. We don't have to use all the edges. But if you did want to use all the edges, here's an example path, EDA, BCA, D. Now just writing that out can be a little confusing, so I will give the advice that when you're doing this, I recommend crossing off each edge one by one to avoid any mistakes you might have. So in this case I said EDABCAD. Well, we'll start with ED, and I put a little 1 there, so I know I used it, followed by DA, 2. And I used the one on the left just because it doesn't really matter. There's no real distinction other than I've used one of them. Followed by AB, then BC, then CA, and finally AD again. And if you'll see that there are 6 edges in this graph, and I've used all 6 of them in this particular path. So that's kind of nice. And again, if you're finding this confusing, I recommend drawing this on a sheet of paper and just crossing them off with a pen or pencil, and it'll make your life a lot easier, I promise. This leads us to our next point, which is Euler paths. Yes, I know that it sounds like it should be Euler, but it's a guy's name. Sorry. Either way, regardless of how you say the word, an Euler path is just a path that uses every edge in the graph. And this doesn't always happen. In fact, it only happens if there are 2 or less vertices with an odd degree. And when that happens, that's a guarantee. So here's an example graph. You can see that A has a degree of 4. It's got 4 edges leaving it, even though 2 of them are going to D. B has a degree of 2, C has a degree of 2, D has a degree of 4, E has a degree of 4, F has a degree of 2, and G has a degree of 4. So because they only have degrees of 2 and 4, and 2 and 4 are even numbers, we know that this has an Euler path. It's just guaranteed. Meanwhile, in this example over here, we can see, well, it has 4 different odd vertices. So C and B happen to have degree 1, and E and A happen to have degree 3. And that's a sure sign that an Euler path does not exist. It's impossible. There's no way. So, in addition to having an Euler path, this actually has an Euler circuit, which is just an Euler path that is also a circuit. You know, it begins and ends at the same place. Now, you could check by just drawing with a pencil and trying to draw the same graph without lifting it, but honestly, it's always going to have a circuit if all of the vertices have an even degree. And if that's not true, then it doesn't have one. It's an exclusive condition. In this case, I've named one such circuit, which sounds really weird to say out loud, but I might as well say AC, GB, EF, DA, GE, DA. That's not the only one. You can find your own. I welcome you to check, but there's going to be a bunch of them. So it's one thing to say that we have an Euler path or have an Euler circuit, but how do we actually know what it is? In this case, we can look at this graph and based on the information that we have, we know that it has to have an Euler path because it has 2 odd vertices. Those are B and G. Everything else is an even degree, and so we have to have an Euler path. But finding it requires us to use a pretty simple algorithm. Step 1 is start at an odd vertex if it exists. And by the way, if it does exist, then there's actually 2. There's no way for it to have 1. And you're going to end up, and the path is going to end up at the other place. And it's a path because you can't have a circuit if there are anything with an odd degree. But then we'll have to consider all possible edges to go to from that point. And we'll then determine if we should take them based on a very simple factor, is that if we remove that edge and it causes all of the remaining edges to be split into 2 sections, we're going to throw that information away. We're not going to use that edge, and we're going to pick a different one. And if not, we're going to add it to the circuit, and we're going to mark it off the graph. Then we're going to keep doing step 2 until there are no more edges in the graph. We're going to move along the path as well. So for more clarification, we could start at something like B. See, vertex B has degree 3, so that's odd. And we could move to vertex C and see how I've marked it there. And then go to vertex E, and then go to vertex D. And I went to C kind of randomly because it didn't destroy anything. It didn't cut the edges off and make it impossible. I then went to vertex E because I had no options. And then I went to vertex D because I had no options. So now we come to our first and only critical point in this whole thing. Well, if we go to take this edge DF, well, then we're going to be stranded on this lower part of the graph and never be able to get back up to this upper triangle piece that we haven't addressed yet. And that would split the remaining edges up. So we cannot go down to F yet. We're going to have to do that later. So instead, we're going to go to A, followed by B, followed by D, and now there's no edges to cut off, so we can go down to F, and finally to G. And that's it. Now, if we had to find a circuit, the same principle would apply, except that we wouldn't have to worry about where we started. And we would run out at the place we started. That's a guarantee. And it isn't actually any different. Normally, this is the section where I go to the next slide, which is just going to say, if you have any other questions, that kind of thing. But the rest of the notes are still going to be posted today. I've just separated them into chunks because of the size of 13.3. It's not too much information, but it is kind of a lengthy series of PowerPoints to go through all the examples. If this section or future sections, because I technically haven't posted this 13.3 video yet, if they're giving you problems, please tell me and I will do my best to help answer them. And if not, I'll see you in the next video. If you have any other questions, you can also email me, message me through Canvas, come to my office hours, which are, once again, by appointment, or you can just drop in on Monday, Wednesday, Fridays, 12 to 1. All I have to do now is just say, have a great day.